According to the nebula formation theory, Earth was formed from a cloud of gas of various elements. As the cloud condensed, it is believed that the heavier metals sank to the center. The inner core is believed to consist of these heavier elements, primarily nickel and iron. The temperature of the inner core can only be determined indirectly from seismic activity in computer models, and it is currently believed that the temperature is about 9,800 degrees Fahrenheit. While in most circumstances this would result in iron acting as a liquid, the intense pressure of the Earth causes iron to act as a solid. Although we have never physically been to the inner core, we can use indirect methods to determine its properties. When an earthquake hits, seismic waves are released and travel through the Earth. There are two types of seismic waves, primary and secondary. Both types travel out radially away from the epicenter. Of the seismic waves, only primary waves can travel through all layers of the Earth. It's this property of primary waves that has given us a peek into the Earth's center. Throughout the 20th century, seismographs, or instruments designed to record seismic waves, were positioned around the globe to better understand seismic waves. Earthquakes occurred, and the seismographs worked as they were supposed to, recording the primary waves. To the surprise of scientists, however, there were two distinct areas on the Earth that wouldn't record primary waves. Primary waves were recorded on seismograms up to 110 degrees away from the epicenter and remained absent until 150 degrees when they would reappear. This is known as a seismic shadow zone, and it provides geologists insight into the properties of the inner core. The change in seismic waves gives seismologists the chance to peer into the layers of the Earth and gain insight into the inner core. Seismologists discovered that primary waves refract or bend as they travel through different materials. They move slower through low-density materials, such as liquids, and speed up as they travel through high-density materials, such as metals. Studies of seismographs have shown that at the outer edge of the outer core, the speed of primary waves drops down to 7 kilometers per second, slowly increasing until it jumps up to 10 kilometers per second through the inner core. Seismologists soon realized that primary waves that traveled through the center of the Earth were arriving faster to seismograms than ones that were not passing directly through the center of the Earth. This realization led them to formulate that the seismic waves passing through the center must be passing through a very dense material, the inner core. The inner core is the dense center of Earth. Theories on the formation of Earth suggest that the inner core is composed of iron and nickel heated up to a temperature of around 9,800 degrees Fahrenheit. Although we cannot directly measure the properties of the inner core, indirect methods, such as how seismic waves interact with the inner core, can give us clues into how it behaves.